Okay, welcome to this, not quite the final session, but it's the afternoon session. I'm going to be talking about a spectral transform test. It's work that I started probably a year ago as part of a CRESTA project. That was an EU-funded project. And I put a few months' effort into porting this code to a GPU and running it on Titan. Some initial work was done on a Cray system called Swan. It's a very small system, like our own HPC GPU-1, very similar size, but it was an XC30. Probably initially it wasn't, but it is now. So this is on. Well, what is this test? Well, I would describe it as a relatively small but important part of the IFS spectral model. Small, probably the total number of lines is between 20 and 30,000 lines, but what is ported is a very small fraction of that, because most of the initialization code, for instance, runs on the host with no reason to port it. It does transforms data between spectral space and grid space via Fourier space, and I'll show you a schematic showing that. Perform some very computationally intensive parts. One is the Legendre transform, which is implemented as a matrix-matrix multiply. Easy peasy, no problems. We should be able to do that. We've shown examples how to run DGEMs on GPUs. And it does today, on a host, it does the OpenMP parallelism over spectral waves. Next would be the Fourier transforms. We've seen how to code those on a GPU. And in the host version, the OpenMP parallelism is over latitudes with their associated fields levels. And between these computational phases are transpositions. I'll explain that when I show the schematic, but this code has an issue with the volume of data that's needed to be communicated in the various stages of the time step. So I'll show that shortly. And what I've done is I have two versions of the code. One is a host version, and the other is a GPU version. I've kept them intentionally separate at this point because I wanted the flexibility to change the GPU version as I learn how to code it better. So I would say that the host version is fixed. It's ready to be given out. But the GPU version, I think, is still not final. And it's, in some respect, there's some work in progress there. The host version, the STT14, has been tested with a Cray compiler, Intel iFort, GNU Fortran, and Portland compiler. Whereas the GPU version is an OpenACC port with cuBLAS, cuFFT, and works with both the Cray and Portland compilers. It's based on the same IFS cycle as the RAPS benchmark, which has already been issued. So somebody who's familiar with taking that RAPS model benchmark, this is the similar style, but it's a much, much smaller code base. As I said, 20, 30,000 lines, and on the same cycle. What's included in this benchmark, this mini app, is a very small, first of all, a very small version that can run on a GPU, single GPU, and moving up a T639 resolution case, which is planned for next year, first quarter, as the ensemble prediction resolution. Then a resolution which is planned for the model, the high resolution model, in next year, in first quarter. This is currently under test here in preparation for operations. And then some interesting future resolutions that are not finalized, but something which I can do with this, run with this test, a 5-kilometer problem and a 2.5-kilometer problem. So cases that will take us into the mid-20s. 10 years from now, if we ever get there. And another high-resolution case is TL7999, which is, again, a 2.5 kilometer case, and that's distressed Legendre transforms. The host version supports a fast Legendre transform butterfly scheme. Instead of doing 2 large DGEMs per wave number, it implements a butterfly scheme which does less floating point operations, and consequently, for the host version, can run faster. That's not been ported to the GPU yet. That would require effectively a deep copy. There's lots of data structures there. I don't really want to hand copy them over the hard way. I'd rather wait for the features to appear in the GPU version. As I said, this GPU port was originally developed in the Cresta project, and I'll be showing some results from running on Titan, which has obviously reasonably old GPUs by today. These packages, this spectral transform test is about 300 megabytes, including all the data for all the resolutions. So it's relatively easy to port or to move between systems. I'll give you an idea of our future. This is the resolution that we will be implementing in the first quarter next year. And this shows the, how the MPI tasks are distributed across the globe. Thank you to Willem for producing this graphic. He's sitting in the front there. So what you see is this is grid point distribution. This is a partition at the pole, and then an increasing number of partitions as we proceed to the equator. So they're supposed to have an equal area, bar 1 grid point, across the globe. This is intended to provide minimum volume in terms of if you're communicating with nearest neighbors. So here we have 1,600 MPI tasks. Each will use 12 threads in operations next year. But we have run a higher resolution model on that, a 2.5 kilometer case, on Titan with 28,000 MPI tasks. So it's 18 times the number you're seeing here. So you pick any one of these boxes, multiply that by 18 inside. You can see that we're getting into some serious MPI parallelism here. I'm not saying it ran well, but it did run, and it did produce the correct results. And this was on Titan, obviously. So let's get on to reality now. Here's the schematic for this spectral transform test. You start off in spectral space with a number of spectral variables. You perform a Legendre transform, transpose the data, that's an MPI all-to-all V. You're in Fourier space, you do a Fourier transform, FFTs, and then transform it again to get it into the grid distribution that I showed earlier, where this each MPI task owns a part of the globe. And you go around through the direct transform. So again, Fourier transforms, Legendre transforms, with the transposition stages in purple here. And you repeat this for 100 iterations. So you start off with some data, you go around one iteration, slight perturbation to the results you expect it to be, can't be exactly the same. You go around again with the same data. Not the original data, but as you saw with the test cases you were running. The more iterations you run, the greater the distance from the original data. We compute some norms to check that the results are correct after 100 iterations, and the norms are within e to the minus 13 or 14 or something like that. So very accurate. So that was very pleasant to see that the GPU version was producing the same results, but it wasn't like that at the start, obviously. I mean, I must admit that at the beginning I had no course on OpenACC, so it was a question of picking up the OpenMP, the OpenACC spec, trying to understand it, and it was fairly well written, so I was very happy to progress with that. Made a few mistakes on the way, but so here's an example of one code fragment, one routine, and not everything is difficult. This case is trivial. You see a doubly nested loop, and there's no transformation to the data. You just stick in your parallel loop and ACC loop, and maybe even the private is not necessarily, I'm not certain. But I put it in there anyway because I come from an OpenMP background, so I like to specify things where I think they need to be. So yeah, easy. And we've seen examples in this class where that was the case. Now, DGEM, actually where I started, I thought let's pick something that's expensive in the model relatively, and see what I have to do to get that running on the GPU. So, well, here you can see at the top is the original DGEM call, and in black in the lower panel, you see what's changed. And effectively, well, originally on the Cray, I had a DGEM underscore ACC, or before that, I just left it as DGEM. And the Cray compiler did actually pick it up, and it worked. But I was getting data from the host, moving it over to the device, running the DGEM, results back to the host. That was the initial stage. And obviously, as the code developed, the data was on the GPU. So here we have the current state with called CUDA DGEM and a host data use device for the three variables, A equals B times C. So here I'm adding a call to a CUDA synchronize, which is a CUDA device synchronize call under that, and a couple of modules which probably you don't need to specify. Probably they're there in the CUDA installation, but I just wanted to see exactly what I needed, so I found this on the web. Basically, it's a cuBLAS module, which is an interface to CUDA DGEM. Like that. So everything linked correctly once I put this in there, and it worked. So I was happy just to use that. And I couldn't put a function into the same module, had to be a separate module. And here's the CUDA device synchronize, which I call CUDA synchronize, which you saw earlier above here. So here we are, CUDA synchronize, returns an error. I'm not even bothering to check the error. Of course it's correct. So that's the use of DGEMs. Relatively straightforward, considering how important it is in terms of the code. FFTs, these were a bit more complicated because when I started, we didn't have an FFTW implementation. We just had what we call FFT 992. It's our own grown FFT package, and which supported just factors 2, 3, 5. I think I said no, 2, 3, 5 factors, and that we clearly could not port that. That was just impossible. So I looked at the QFFT documentation, and originally I had a CUDA routine which created the plan and just executed the plan. That was the easiest approach. And then this evolved into a case where I created the plan separately in initialization, or the first time it came across a particular vector length for the FFT, it would store away the plan ID, and then next time you wanted to execute the same length and lot size, it would immediately return that plan ID, and then you could execute that plan. So again, it uses this ACC host data. Straightforward, no surprises, which actually there was a benefit in doing this because at the same time we developed a new grid which did not have just factor that for FFTs required non-prime factors which were other than 2, 3, and 5. So we switched to FFTW fairly quickly as a result of this work. I could use the same code effectively as I already had used on the GPU. But I didn't take the next step where I could use the CUDA FFTW compatibility feature. I said that's an option to do in the future. And this is my execute plan FFTC routine, CUDA, very simple. Depending on the input sign, I will execute the real to complex or complex to real. Very straightforward. And I do a device synchronize after the call. I'm not showing you the actual the error checks in here. Check all the return arguments that could possibly be returned from the FFT call. This is the CUFFT safe call. Strategies. Well, I think there's nothing surprising. We've learnt this during this this class. You've experimented with the small toy codes. I did exactly the same. I started off with a molecular dynamics code, 300, 400 lines, ported that within a week. It took a bit of time to understand what was the most efficient approach. And once you've got some experience with OpenACC, move on to a working version of the host. The host version, adding more diagnostics, etc., and then port one or two routines to the GPU and gradually move out to the whole code. So you've got to start somewhere. I don't think you can just take the whole code, sprinkle on a lot of ACC directives, and expect it to work. You've got to start somewhere, and I started from something computationally intensive and moved out. So in some respects, I was doubling the work every time because the data was either on the host or the GPU, and at some point I was a bit confused as to where it was. So it ended up okay in the end. And of course, the directives like update host is great for always getting you out of trouble. If you bring the data back to the host, look at it, compare it against a host version, you know if the data is correct or not, you can proceed. So it's rather straightforward. Always check the results are correct. You know, there's always a question of what are the correct results. And as has been said, it's pointless to focus on performance until the whole code is on the GPU. So that should be obvious, obviously because of the copies. Use MVProf and MVPP. Well, I did that rather late into the day, and use async where possible. All the things that we've covered in this class. Well, here's an example of a small code, and I wanted to show a case where we're running through all the this is focusing on the all the computationally intensive parts of the code and the cost of the time step in total. And here is a case where we have 800 vectors, or a lot size of 800, and I'm comparing one of our Cray 24-core Ivy Breach nodes against a K20X. And obviously this is times in milliseconds. So we can see that the Cray, the host version is running very much faster. And the total time per time step, it's obviously faster. 198 is faster than 256. Now, I increased the lot size, how many fields I process with this case, and suddenly it's reversed. The GPU is actually doing better. So it's a function of how much work you introduce. Either it's a case of the vector lengths being longer or the lot size. You've got to have some substantial compute problem, to be able to expect a case where the GPU is faster. It's not automatically faster. So that told me something. This table, or this chart, shows the run on a GPU on the Titan system. It's the spectral transform compute cost again. I'm looking at the main computational areas, and the milliseconds per time step is on the vertical axis, and I'm looking at the expensive computational parts. So, as I said, the Legendre transform, inverse and direct are DGEMs effectively. They come down to that. The Titan version with the GPU effectively was running 2 or 3 times faster, doing well, fine. Well, we happy with that. But the Fourier transforms were not. They were just, well, I'll say a bit faster, but one expected them to be a bit faster at the time. The reason for this was at this time I had a CUDA bug which prevented me from creating the plan separately from the execution. So that's now in place. Unfortunately, I don't have access to Titan to repeat this case. So this is a fairly large problem size. So I expect if I were to rerun this again, it will be faster. But I don't want to say how much. I wouldn't know. It's only a guess. So good news. Large problems on GPUs seem to give some good performance. And then I'm looking at the FFTs in particular for a lot size, which is approximately the size that we would use today on EXE30. And what I'm comparing here is a vector length, or FFT length, latitude points, of increasing size. And I've mentioned here at the bottom for our operational resolution next year, the maximum latitude would be 5,000, so around here. And what I'm seeing, I'm looking at the old FFT992 case, which is the purple line, in terms of cost, that's the increased resolution, or the FFT length, and FFTW. Now you notice that FFTW costs have these big spikes, and that's because you've got these large primes in there, and I've just tried to show you that here is 3700 point, whose length is 3700. Well, obviously it's prime up to 100, and the 37 is non-prime. And you can see 41 equally non-prime. So this is why you see the spikes. And I exclude the FFT992 case for those data values because clearly it can't run those. Now the GPU version is costing more, and the reason for this, there's two versions there. One is where we have a change of order of the leading dimension. That's quite important for FFTs. The version 2, which requires a transpose, and including the transpose, does better, so that's the version I'm using. But it's still costing more than the FFTW. And this is due to this lot size issue. I'm not giving it enough vectors. And the lot size is something which I'm trying to be realistic here, but I think that like some other systems, like on a vector supercomputer, you always wanted to have long vectors. Well, I think on a GPU, you want to have a larger number of fields. And we can accommodate that with a parameter setting in IFS. It's NPRTRV. In this spectral transform, we do a 2D decomposition. Well, here, I'm doing a 1D decomposition, and it ends up being faster for a GPU. This NPRTRV will be 1. So in the inverse direction, we've got something like 800 fields, which is good. So coming towards the end here, this is showing a similar thing where we're increasing the resolution. So I'm going through all the latitudes for Fourier transforms on this scale, and then increasing the number of fields. It's very hard to see in some respect that you've got to have either a higher resolution or a large number of fields to process to get a case where the GPU is faster than the host version. And as a table, it's shown like this. So resolution, different resolutions at the top, and lot sizes. And you can see that for this case where we would have this more optimal partitioning for a GPU, we can get 1.4 times or 1.35 times faster than the host. And the host is 24-core Ivy Bridge. Where it drops down, I don't know why, but to be investigated. So experience, there's a higher OpenACC programming effort compared to OpenMP. I tried to correct the number of directives that I quoted before when I presented this last October. I'm not including the end directives, and I'm not including continuation lines, so real directives. 16 has gone to 162 in 18 routines. So 8 routines before with such directives to do this test, and 18 with the OpenACC. So there's more work clearly to be done with OpenACC by my measure. Most of the porting time spent on this, the FFT interface, thinking about it, how to get it to run with CUDA FFT. Easy to say, yeah, it's obvious now, but when you don't know, it can be very cloudy. Yeah, fine. Performance issues. I think that the GPU version could very well be faster. And this is just shows some a case where I showed before a high-resolution case. It's 2.5 kilometer case with 800 fields. And where I've marked it in this sort of yellowish color thing are these are the computational phases, communication phases, and the actual transfers between host and GPU. And here's the cost on the XE30, the GPU time, and if I had a GPU with an XE30, here's what the time would be. The reason that this is different is because I've introduced async into the Legendre transform. There's two big DGEMs. I can do them at the same time with async, and that works well. There's a good improvement because of that. I can't do much about the communication, but I've also improved the host to GPU, GPU to host communications, but I don't know the times on Titan. So without these improvements, we were running a little bit faster on, say, a theoretical K20X XE30 system compared to just a pure host version. So yeah, the GPU could be faster. And it will use, what, half the power as well compared to the, I think I saw it somewhere. So from a power point of view, it is efficient. Okay, that was it. Sorry for being so, probably too much detail, but Christian.
Since you're saying that there's not enough work, does this mean that you have a way that you can add more work in terms of physics, chemistry, etc., very little extra cost in one GPU?
Well, this has no physics here. This is, I think it's a case similar to the physics. You could say we could add more fields to be transposed. If you really wanted them to go to spectral space from grid space, then it's better to have more than not. So currently we do 3 variables in the direct and 6 on the in the inverse. These are 3D variables. So more is better for a GPU.
For the physics question, geometrically the transforms and the physics direction are not right.
There was a more general question whether by having, in essence, a lot of compute power available, you might be able to do something which we can't do on current architecture because it would come for a very little extra cost.
Yeah, I think if you look at in BBP, you can see that for a T159 problem, it's very small. It runs in a single GPU. There's no communication. So the whole time step, 100 time steps, actually no communication with the host other than these 4-byte quantities, which occasionally see. And we've only got 25% of the GPU being used because a number of places where we've got a small routine, there's hardly any work. At the kernel startup, maybe 4 bytes are transferred. Who knows what that is? It's not clear. Maybe it's the length of the vector or something in a do loop or something like that. That's where there's some further investigation is required to eliminate these. There's still a large number of hosted device copies, but they're very small, 4 bytes or 8 bytes.
Was that with Cray compiler? Or?
With a Cray compiler, yeah.
Because I've seen that also.
Yeah. I see it with the Portland compiler as well.
Okay.
So it's not just that. So, okay, thank you.